Today we will start with the transport phenomena in furnaces, the second part, that is the heat transfer. As I have repeatedly said, a furnace is a thermal enclosure and is employed to heat the raw materials to the process temperature and to carry out the functions like roasting, smelting, sintering, refining, converting, heating, and so on. In all these functions, it is important that the transfer of heat from the flame to the walls of the furnace takes place at a uniform rate, so that the furnace and the charge, they are heated to the desired temperature. So, for example, if we consider a combustion chamber of a furnace which is lined with the refractory material, and here we have a burner, and this burner produces a flame, and here we have the charge. So, this is the flame, and the products of combustion transfers its heat to the charge to the combustion chamber and hence heated up. Part of the heat is also transferred to the surrounding, and hence heat losses are important. Therefore, for an efficient furnace design, it is important to consider the various mechanisms of heat transfer. If we see this particular combustion chamber of a furnace, then this is a flame, and here heat is being transferred. Heat is transferred by radiation and convection. Similarly, part of the heat, it is also transferred through the refractory lining and to the surrounding. So, this particular transfer of heat from the combustion chamber to the surrounding, that is by the conduction. So, in efficient design of furnace, it also requires a fairly good knowledge of the heat transfer mechanisms, and as we look the heat transfer mechanisms operative in a furnace, they are conduction, convection, and radiation. In fact, conduction, heat transfer occurs by transfer of vibrational energy from one molecule to the other one. In case of convection, the fluid flow is important. It is the flow of the fluid, or it is the velocity of the fluid that carries hot packets of fluid to the colder part and colder to the hotter part for the efficient heat transfer to occur. In case of radiation, there are electromagnetic, that is, heat is transferred by electromagnetic radiation. When a surface is irradiated, part of the heat is reflected, part of the heat is transmitted, and part of the heat is absorbed. So, all these three mechanisms are operative in the design of the furnaces, and from the efficiency point of view, from the energy conservation point of view, it is important that we understand fairly well the role of heat transfer. So, let me first start with the conduction. Now, as I said, that conduction involves the flow of heat by transfer of vibrational energy from one molecule to other. As the heat transfer occurs, in the beginning there will be unsteady state, and at a steady state the flow of heat from high temperature to lower temperature occurs, and the flow of heat is proportional to the temperature gradient. All of us, we are aware with the so called Fourier's law of conduction. So, I am straight away writing at steady state, by this I mean when temperature is not a function of time, however temperature is a function of the coordinates, that is x, y and z. So, at steady state, for example, if you are consider the y direction, then heat flux that is equal to minus k into dt upon dy, where k is the thermal conductivity of the material, and T is the temperature, and in fact dt upon dy is temperature gradient, and Qy is the heat flux. If we say Q, that is equal to heat flow, Q is equal to heat flow. So, and so this is what is the Fourier's law of heat conduction. That is, in short, it says that heat flux is proportional to temperature gradient. Whereas, if you want to write down this expression in terms of Q, which is the heat flow, then Q will be equal to K into area. That is Q, that will be equal to minus K A dt upon dy, where Q is now the heat flow, that is in watts, and A is the area, and remember this area is perpendicular to the direction of flow. So, now similar expression we can write down in all the three rectangular coordinates. So, if you write down that, we can say that Qx that is equal to minus K delta T upon delta X, Qy that is equal to minus K upon delta T upon delta Y, and Qz that is equal to minus K delta T upon delta Z. So, that we can write down Q that is equal to minus K into del T. So, this is the Fourier's law of heat conduction in 3 dimension. Now, one thing you should note that Q is equal to minus K, and the minus sign is resulting because the heat flow from the high temperature to lower temperature. So, now what we are telling here is that this is we are considering thermal conductivity say of the material, it depends on temperature, and it also depends upon porosity, and it also depends upon isotropy, whether the material is isotropic or anisotropic. So, in isotropic media, K is same in all direction. As regards porosity is concerned, lower is the porosity, higher is the thermal conductivity, and higher is the porosity, lower is the thermal conductivity. We can define another term from here, is that thermal diffusivity. thermal diffusivity, and thermal diffusivity is defined as alpha, that is equal to K upon rho into Cp, where the dimensions of alpha, that is equal to meter square per second. So, the thermal diffusivity signifies the diffusion of heat into the system, where K is again thermal conductivity, rho is the density, and Cp, that is equal to specific heat of the material. Also, one number is important, say the ratio of kinematic viscosity upon thermal diffusivity, that is called PR, where PR is equal to Prandtl number. Prandtl number, and this is the kinematic viscosity. Kinematic viscosity, and that is equal to mu upon rho. So, if we substitute, then we get PR, that is equal to mu into Cp upon K. So, this Prandtl number is also a very important dimensionless number in case of studies on the heat transfer. Now, the value of K, which is the thermal conductivity, it can vary from about 0.01 watt per meter Kelvin for gases to 1000 watt per meter Kelvin for metals. So, in the Fourier's law of heat conduction, you note that heat flux is equal to K into dT by dy. This is a very important equation, and this interconnects the heat loss and temperature gradient that depends upon the property of the material, that is the thermal conductivity of the material. Based on this calculation, one can design the different materials with different thermal conductivities as required by a particular equation. So, this particular expression, that is the Fourier's law of heat conduction, is very, very important. Now, as I already said, K depends on temperature, porosity, and also K for ceramic material. K for ceramic material is much lower than metals. Now, let us say the units, that is important. So, I will write down just summary of units. Here SI units, here CGS units, and here FPS units, that is British system, foot, pound and second. So, QY SI units is watt per meter square, calorie per centimeter square per second, and in FPS system, that is BTU per hour feet square. Temperature, that is expressed in Kelvin, here it is degree centigrade, here it is degree Fahrenheit. Distance Y in meter, it is centimeter and it is feet. K watt per meter Kelvin, here calorie per meter second into degree Celsius, here BTU hour feet degree Fahrenheit. Cp joule per Kelvin into kg, here it is calorie per degree Celsius gram, here it is BTU feet per pound. Then alpha, which is the thermal diffusivity, it is expressed meter square per second, centimeter square per second and feet square per second. Then mu, which is viscosity, Pascal into second, here it is gram per centimeter second, here pound m upon feet into hour. So, what I thought that these units are sometimes very important in order to understand the heat transfer from various books, because there are various books are written. Some books they express in BTS or in BTU units or in FPS system, some in CGS and some in SI units. So, now let us take one very simple problem. For example, at steady state, the temperature profile, in a laminated system is shown below. This is just a problem for thinking. So, the profile is as follows. Now, here this is the temperature and here is the distance in the x direction. Here you have the temperature T1, this is material 1 and this is material 2. Now, the temperature gradient is this one, this is T2 and here it is T3. Now, suppose thermal conductivity of material 1 is K1 and thermal conductivity of material is 2 is K2. Now, which one of the following statement is correct? Which one of the following is true? A, K1 equal to K2, B, K1 less than K2, C, K2 less than K1. So, you have to answer this question and you note that there is a steep temperature gradient in the material 2, therefore, the statement C is correct. C is correct. C is correct. Now, you can see in terms of Fourier's law of conduction, because K is low, the temperature gradient is steep. So, that is why the answer for this is this one. Having studied Fourier's law of heat conduction and having seen the expression between heat flux and temperature gradient, which is related by thermal conductivity of the material, we are in a position now to study heat flow through a composite wall. A composite wall means a wall which is constructed by refractory materials of different thermal conductivity and different thicknesses. Now, such a composite wall construction is very, very important in case of furnace design. In the furnace design, it is often required to construct the walls of the furnaces of the different type of refractory depending upon the need. As I have already pointed out, in my earlier lectures on refractory material, that refractory must be chosen as per the metallurgical objective. Now, let us see this heat flow through a composite wall. With this I mean, so let us consider this is a composite wall. I am just drawing a sketch for you. So, this composite wall is constructed having three different type of materials: material A, material B and material C. Material A have the thickness delta XA, this is thickness delta XB, and this is as a thickness delta XC. Material A has thermal conductivity as Ka, this is as Kb, this is as Kc. Now, this particular composite wall is exposed to the fluid at different temperatures. So, the material which is having A is exposed to the combustion chamber of the furnace, and as such let us have this, the temperature of the furnace, for example here is as Ti, this is the furnace combustion chamber. And the other side is facing to the surrounding, facing to the surrounding of temperature T0. So, now if we wish to represent the temperature profile, then from here, say this will be here. So, this is the temperature, let us say it is T1, there is a gradient, let us take this temperature as T2, this temperature as T3 and this temperature as T4, and from here it again goes to the surrounding which is T0. So, this is the temperature profile and the flux Q is passing and the flux Q will be equal to out. So, that is what the composite wall. Now, we are required to find out an expression through which we can calculate the heat flow through this composite wall. Now, there are several approaches to find out the heat flow. Now, one approach is, approach number 1 is doing heat balance over a volume element of thickness say delta x. Now, this heat balance we have to perform for each material, and then we have to substitute the Fourier's law of heat conduction and get the temperature gradient and so on. So, this is one approach. You do heat input is equal to heat output in each material, and then simultaneously solve the equation and you get the heat flow through a composite wall. Another approach is that utilize the generalized energy balance for conduction. Utilize energy balance equation for conduction, and generalized equation for conduction is say rho Cp delta T upon delta T, that is equal to K into del square T. So, this is also another approach through which you can proceed to solve this particular problem. Now, the third approach is the so called thermal resistance approach. Third approach is thermal resistance approach. Now, in the thermal resistance approach, electrical analogy is used to find out the heat flux. Now we all know that the flow of current, that is equal to potential difference upon resistance. So in an analogous fashion, we can also say heat flow that is equal to thermal potential difference, divided by thermal resistance, So all that now, the thermal potential difference is the temperature between the fluid, which is the temperature facing the walls of the composite construction, that towards the furnace and towards the surrounding, and by calculating the thermal resistance we can find out the heat flow. Now let us sum up the assumptions are. The one assumption is that we are considering one dimensional heat flow. One dimensional heat flow at steady state. This is the one dimension, one assumption, and second assumption is that we are assuming perfect thermal contact between the various materials of construction. With perfect thermal contact means there is no air gap between the two material. So now, since this is a steady state, heat cannot be accumulated, so therefore heat flow across each wall should be same, and because heat flow across each wall should be same, the temperature should drop depending upon the thermal conductivity of the material. So straight away we can write down heat flow, that will be equal to Hi into A Ti minus T1, that should be equal to minus Ka into A T2 minus T1 upon delta XA, that should be equal to minus Kb into A T3 minus T2 upon delta XB, that should also be equal to minus Kc into A T4 minus T3 upon delta Xc, and that must be equal to H0 A T4 minus T0. Now note here Hi and H0 are heat transfer coefficient, Now this Hi is the heat transfer coefficient from the combustion chamber to the wall of the composite material facing the combustion chamber. So it is important here to note that this temperature T1, T2, T3, T4, they are the temperature of the respective walls. Similarly, H0 is the heat transfer coefficient from the outer wall of the composite to the surrounding. Now, solving this equation simultaneously, we arrive that Q, that is equal to Ti minus T0 upon 1 upon Hi into A plus delta Xa upon Ka into A plus delta Xb upon Kb into A plus
delta Xc upon Kc into A plus 1 upon H0 into A. So, let us say this equation is number 2. Now, remember this 1 upon Hi into A and 1 upon H0 into A, they are the convective resistances. They are the convective resistance to the heat flow, whereas delta Xa upon Ka into A, delta Xb upon Kb into A, delta Xc upon Kc into A, they are the thermal resistance. They are the thermal resistance offered by the walls of different thickness and different thermal conductivities. Now, from this we can consider that heat transfer rate is as a flow and the combination of K, delta X and A as resistance to heat transfer. So, if we want to represent the whole thing by its electrical analogy, then what we can say that this is the one resistance, here the temperature Ti and the resistance over here is 1 upon Hi into A. So, this temperature is then T1. This temperature is T2 because of the resistance delta Xa upon Ka into A. Similarly, your third, and this temperature is T3, resistance is delta Xb upon Kb into A. Now, fourth wall, this is as temperature T4 and the resistance is delta Xc upon Kb into A, and ultimately we have a temperature T0, and this is the resistance represented by 1 upon H0 upon A. So, all the resistances, they are in series. So, here all the resistances are series. So, all resistances are in series and they can be added to get the equation number 2 as we represent. So, this particular representation, it can be considered as this is an equivalent electrical circuit. Equivalent electric circuit of heat flow through a composite wall. Through a composite wall. So, now all the resistance can be added up and one can obtain the so called Q, that is the heat flow. So, the thermal resistance now, thus total thermal resistance, that is equal to 1 upon Hi into A plus delta Xa upon Ka into A plus delta Xb upon Kb into A plus delta Xc upon Kc into A plus 1 upon H0 into A. So, this is how the heat flow through a composite wall is. Now, with this expression, one can design the composite wall of different thermal conductivity and different thicknesses. One can optimize them, that well, if this is the thickness I want, what should be the K I should use it, or if I know the value of K, what should be the value of delta X. So, this is a very important equation for the design of the walls of the, for example, rectangular furnaces. So,
what we have considered is a rectangular wall construction of different material of different thermal conductivity and different thickness, but there are also tube furnaces which are cylindrical in nature. There are also duct which are also cylindrical in nature, and they are also required to be insulated. So, as such, next thing we will consider the heat flow through a composite cylindrical wall. Heat flow through a composite cylindrical wall. Again, here we will consider one dimensional heat flow. One dimensional heat flow, that means the gradient is along the thickness of the wall, that is one. Second, we will assume a steady state. We will assume a steady state, that means here temperature is a function of, say, function of radial coordinate. Since we are considering one dimensional, so temperature is a function of R only. Other dimensions we are considering as a uniform one. Third assumption is that assuming a perfect thermal contact. Perfect thermal contact. However, it is easy to assume over here, but it is very difficult to maintain a perfect thermal contact, because the surfaces of the refractory will always be rough, and as such a perfect thermal contact can be achieved nearly, but cannot be achieved in an absolute sense. Now, the reason why I am mentioning over here, because if there is not perfect thermal contact, there will be air gap. In the calculation, we will consider perfect thermal contact and hence no air gap. So, when we will apply this calculation or the result into the actual practice, then this may not tally 100%, because in the actual practice the assumption of perfect thermal contact may not be valid. There is always an air gap, and air gap has a very, very small thermal conductivity, as in the later I will show you through a problem that what this thermal conductivity means. So, that part is to be considered very carefully. What I mean to say here, that what assumption we are making, that should also be considered by applying the result in the actual practice. So, now let us consider, say, a composite cylindrical wall. Say this is, for example, one, this is the second, and this one is the third. So, let us see, this is the radius R1, this is the radius R2, and this is the radius R3. Now, if I want to draw the temperature profile, somewhere here, this is the one temperature at this interface, this is the temperature here at the interface. So, the temperature profile somewhere here, this R1 is facing to the furnace. So, here if I have the temperature Ti, then the temperature will drop here, and this temperature, let us say, is T1, this interface temperature is T2, and this interface temperature is T3, and from here it goes to the T0. So, here you have heat transfer coefficient Hi, here you have the heat transfer coefficient S0. So, this is in fact a steady state temperature profile. A steady state temperature profile through a composite wall of thickness or different thicknesses and different thermal conductivities. So, let us take the conductivity of this is K1 and this conductivity of this is K2. So, we can also draw the thermal circuit. The thermal circuit analog to electric circuit, all that we are assuming that the walls of different thickness and different thermal conductivities offer resistance to heat flow, same as the resistance offer the flow of current. In the same way, the resistance offered by the brick, it rather hampers the heat flow through the wall. So, if we want to represent the thermal circuit, then for example, here somewhere we have temperature Ti, then we have 1, say the resistance which is 1 upon Hi into 2 pi L into R1. Note that the wall which is facing the furnace, heat transfer coefficient correspond to the diameter or the radius of that particular wall. Now, here because of the resistance, temperature has come to value T1, then now it meets the walls of different thickness. So, here I have got temperature T2 and the resistance is ln R2 upon R1 divided by K1 2 pi L. Now, because of the say third wall, I got here the temperature T3. So, this resistance is ln R3 upon R2 divided by K2 2 pi L, and ultimately it through the surrounding, this is the T0, and here it is 1 upon S0 into R3. Note this side is refers to the diameter of the or the radius of the wall that is facing to the surrounding. So, now it is very simple, all the resistance are additive because this is in series. So, we can represent now applying series concept, we get say heat flow Q that is equal to Ti minus T0 upon 1 upon 2 pi L R1 Hi plus ln R2 upon R1 divided by 2 pi L K1 plus ln R3 upon R2 divided by 2 pi L K2 plus 1 upon S0 into 3. So, this is the heat flow Q through a composite wall of thermal conductivity K1 and K2. If we have 3 or 4 wall, accordingly we can add the resistance term. So, from here we can say that the thermal resistance for a rectangular wall in one dimension, the thermal resistance is RT, that is equal to delta X upon K into A. If we have cylinder in one dimension, or you can say for infinite cylinder, RT that is equal to ln R2 upon R1 divided by 2 pi L into K,
and thermal resistance from surface to fluid that is equal to RT, that is equal to 1 upon A into H. So, this is how the concept of the thermal resistance is. Now, let us apply this equation. So, as such I will say application of heat flow equation to refractory lining design. Now, let us first let us consider design of multi-layered refractory lined furnace wall. Now, we are considering one dimensional heat flow. So, let us consider a furnace wall having 3 different type of material. Just drawing this sketch. So, this is temperature given as T1, this is temperature T2, this is temperature T3, here is temperature T4 and here is temperature T5. Now, the wall, so this is the one wall, second, third, and this is the steel shell. This is the steel shell and whose thickness is 3 millimeter, right. So, this is wall 1, wall 2, wall 3. The thickness of this wall is 250 millimeter. Thickness of this wall is 140 millimeter. Thickness of this wall is 45 millimeter. K1 that is equal to 1.1, K2 0.75 and K3 that is equal to 0.08, all in watt meter Kelvin. K of the steel shell, K steel shell is given to you 45 watt meter Kelvin. Now, if I represent the temperature profile, then inside the material it will be linear and this faces to the temperature. Let us consider this is the temperature of the furnace, this is the temperature for example of the furnace Ti, that is equal to 137 degrees Celsius and Hi that is equal to 26 watt per meter Kelvin. So, as such there will be temperature drop, this will be Ti, and here accordingly we have T0 and here H0 is given to you 5.9 watt per meter square Kelvin. So, this is how a multi-layered lining of different thicknesses. What you have to calculate? You have to calculate first of all the amount of heat flow. So, calculate heat flow, and also calculate temperature say T1, T2, T3 and so on at each interfaces. So, this is what the problem is. How will you calculate now? So what we have to do, first of all we have to calculate the heat flow. So we will calculate thermal resistance. We will calculate thermal resistance, that is A into RT. I already given the formula. So if you calculate thermal resistance, that will come out to be equal to 1.18 meter Kelvin. So from here I can calculate the heat flux Q, that will be equal to Ti minus T0 upon 1.184, that will be equal to 904 watt per meter square. This you can calculate and you will get the answer. Now you have to calculate the temperature at different interfaces. The thermal resistance offered by each layer, you have to equal it with the heat flux, because heat flux cannot change. So for example, the Ti minus T1, that is equal to Q upon Hi. Similarly, Ti minus T2, that is equal to Q upon K1 upon 0.25, and similarly you can proceed. So you will be getting the temperature T1, that is equal to 1135 Kelvin, temperature T2, that is equal to 1130 Kelvin, and temperature T3, that is equal to 961 Kelvin. Similarly, you can calculate temperature T4 and T5, and all these temperature can be easily calculated, because heat flux through each material will be same. So all that you have to equate the thermal resistance offered by each wall with the heat flux. So only unknown is T1. So Ti is known, one can calculate T1. Once you calculate T1, then T1 minus T2, here T1 is unknown, T1 is known and T2 is unknown. So that way one can calculate the different temperature. Further example I will take in the next lecture.